Okay, dear participants of the 6th Geometry-Topology Summer School, our final speaker today is İzzet Coşkun from University of Illinois, Chicago. Thanks him for accepting our invitation. As a he's our scientific and also organizing committee, so thanks for giving time for us to tell this stuff. Go ahead.
All right, thank you very much. Thanks all for being here. So in these lectures, I'll talk about the normal bundles of curves and how that affects geometry and how we can say something about these normal bundles, and using that we can get information about the geometry of varieties. So I'll start with rational curves and in projector space. So let's start what we can say about that. So what do we mean by a rational curve? There are various things we can mean, but for first approximation, we are going to say a rational curve is a map from P1 to Pn, from projective line to projective space. Such a map is given by a collection of n+1 polynomials of degree d. And of course, if you want this thing to be a morphism rather than, a rational map, then you need to assume that these n+1 polynomials that you have no common roots. So let's do some examples so that we see what we are talking about. So like the simplest rational curve in projective space, of course, is a line. And the way you can think about this is that, you can send ST, for instance, the ST, 0, 0, 0. And then, that's the line x2 through xn is 0. You can have a conic, right? So, conic in projective space. So the way you can think about that, again, is as a map from your ST coordinates to, say, for instance, S square, ST, T square. Then, of course, this satisfies the conditions, the x3 through xn are 0, and then, this times this is the square. So x0 times x2 is x1 square. And then, there's a generalization that's called the rational normal curve. For example, in P3, it goes to s cubed, s squared, t, st squared, and t cubed and zeros. And that has the relations that x0 times x2 is x1 square, x1 times x3 is x2 square, and x0, x3 is x1, x2. Anyway, so we are talking about something like this. A rational curve for us will be a map from P1 to Pn. And, you can say a bunch of things. Maybe we just care about the image and not the map itself. And that's usually will be the case. We just only care about the image. And so we'll think about this up to reparameterizations of the map. And then, you can also like quibble whether we want these curves to be smooth, singular, or what kinds of singularities to have. And I'll make some remarks about that. But to a first approximation, you can think of it as an embedding of P1 and Pn, at least if n is at least 3. All right, so we can count the dimension of the space of such maps, right? So at the end of the day, what is this data? This data is I need to give you n+1 polynomials of degree d. So we want n+1 polynomials of degree d. These are in coordinates st. Well, how many polynomials, what's the dimension of the space of polynomials of degree d? Well, I just need to specify the coefficients of d plus 1. So I need the coefficient of sd minus 1t all the way to td. There are d plus 1 coefficients to specify. And then I have n+1 polynomials. So that you see that we have n+1 times d plus 1 dimensional space. But of course, if I simultaneously scale all the polynomials, I don't change what happens, right? In projector space, you can simultaneously scale everything. So I'd better subtract 1. And then, I don't want to think about the reparameterization. So PGL2, right, acts on P1 by, changing coordinates. And we don't want to say that the rational curve is different if you've changed coordinates. So you have to subtract another 3 for that. So that you see that the space of rational curves of degree d and Pn is n+1 times d plus 1 minus 4 dimensional. And it's an irreducible space. It's basically, you can think of it as a quotient of an open set in a vector space. All right. But you see, often what you want to do is you want to compactify the space, right? I mean, it's helpful to have a compact space to work with. And there are two standard ways of doing this. One is you use the Hilbert scheme. So it doesn't matter if you don't know what the Hilbert scheme is. Let me say a few words about it. So what you do is you take your locus of smooth rational curves, right? At least if you're in PN with n at least 3, right? You take your locus of smooth rational curves, and then you see this lies in the Hilbert scheme, and then you take just the closure of that locus. So that gives you some sort of compactification. The nice thing is that it gives you some projective scheme containing all your smooth rational curves. But the problem is that the Hilbert scheme is often fairly complicated. The boundary is not well understood, and there may be many components, and we'll see some examples. So it's not such a convenient space to work with. There is a nicer one in this case introduced by Kontsevich, which is the following. So it's very similar to the spirit of what we talked about. So what you do, this Kontsevich space, what it does is it parameterizes a curve together with a map. It doesn't have to be genus 0, but since we are talking about rational curves for now, I'll stick to genus 0, right? So what you do is you take a P1 and you look at a map just like we did into Pn. Again, the target doesn't have to be Pn either. We can change the target, but since we are talking about rational curves in projective space, that's what we have. And then you see, typically what you have, of course, is you have a map from a smooth curve into Pn of degree d. But so how do you compactify the space? What you do is you allow the curve to break. You allow the domain curve to become reducible. So what you do is you look at reduced nodal connected curves of arithmetic genus 0. So that means that you have a chain of spheres like this that meet transversely at each of the points that they meet, and only 2 meet at a point, right? So you look at the tree of P1s together with a map to Pn. And then there is one condition that you have to impose on the map to get the good space. You see, if this has infinitely many automorphisms, then you don't get the good space. So you require that it has finitely many automorphisms. In other words, in order to compactify, instead of looking at maps from one P1 to Pn, what you do is you allow trees of P1s and a map from a tree of P1s to Pn, except that you want to specify that it has finitely many automorphisms. But that is, again, relatively easy combinatorial condition to check. So suppose that you have a map from something like this, a union of P1s, if the map is constant on a component. So in other words, this component maps to a point in projective space, then what you need to have is that you need to have at least 3 nodes. At least three nodes. And this, you see, this pink curve now has 3 nodes. It's meeting the curve in 3 other points. So that's fine. So the map can be constant there. And if the curve does not have 3 nodes, then the map is not allowed to be constant. Okay. So again, the reason for that is that the automorphisms of P1, right, is PGL2. And, it acts by linear fractional transformations. And we know that linear fractional transformations take any 3 points to any other 3 points. But once you fix 3 points, then, then it's the identity. So that, that kills the automorphisms. And in this way, so you get the nice compact space. You see, if you didn't pose a condition like this, then you could always add like more and more and more P1s and make the map 0, and it wouldn't be a finite space. So that's why you need something like this. All right. So in other words, what is the space? So the general point of the space is a map from P1 of degree d, right? And it's typically an embedding as soon as n is 3, right? Which is the space that we started with. And on the boundary, what do you see? You see like, some reducible domain curves. And typically what it will have only 1 node. And then the degree on this one component will be degree I. And the degree in the other component will be d minus I, so that it will break into 2 pieces. I mean, of course, more complicated things can happen. So the map can, like, you know, the domain can break into 3 pieces. It can break into many pieces, like, so, you know, first of all, the image doesn't have to be smooth. We don't control the image, right? So like you could have maps where the image crosses itself, or like the derivative vanishes, and so on and so forth. But the nice thing about this space, so let me jump ahead a little bit, this space is irreducible. This conserved space is irreducible. And in fact, it turns out to be irreducible for a large number of target spaces. So for instance, whenever you map into a homogeneous variety, G mod P, right, things like Grassmannians and flag varieties and things like this, then this space turns out to be irreducible and of the expected dimensions, so that, like, you know, it's much easier to work with than the Hilbert scheme. All right, so maybe let's do a few examples rather than keeping this kind of thing very abstract, right? So if the degree is 1, right, if the degree is 1, then you see like the only possibility is then the maps into Pn is a degree 1 curve, so that then you get a line. So in other words, in this case, both the conserved space and the Hilbert scheme are the same, and they have a nicer description. It's called the Grassmannian. So this is the space that parameterizes lines, okay? If the degree is 2, right? So then the way you should think about it is the conics and projective space, right? The general point of the space is a smooth conic, right? I mean, we've seen an example of something like that already. So let me go up. It's something like this, right? St goes to s squared, stt squared, and you sum zeros, so that it's a nice conic. It's given by the equation x naught x2 minus x1 squared is equal to 0, and some linear equations, okay? But already here, the Hilbert scheme and the conserved space differ. The Hilbert scheme in this case turns out to be actually not that hard to describe. So any conic in the plane, in Pn, turns out to be a planar conic. It has to be a degree 2 equation in the plane. You need to check that, but it's true, right? So then what it boils down to is that you need to specify a plane. So specify a plane. And in the plane, you need to specify a conic. And of course, in the plane, the conic typically is a smooth conic, but then of course, you know, it can break into a union of 2 lines, or it could even become a double line, okay? But the key point here is that they are always planar. So in other words, the way you can think of this Hilbert scheme in this case, right? You know, you choose a plane that's parameterized by the Grassmannian, and in the plane you choose a degree 2 equation that vanishes, and you know that's parameterized by a bundle. If you want, the bundle some square, the symmetric square of the tautological bundle. So what's a quadratic form? So a quadratic equation is like, you know, like quadratic equations are symmetric squares of linear equations, right? So the Grassmannian has a tautological bundle. Given a plane, you can associate a plane to it, namely the plane itself, right? And now if you look at the dual of that, so those are the linear forms on the plane, and then the symmetric square of that thing is quadratic forms on the plane, yeah? So that you can think of this Hilbert scheme as being, you know, a projector space bundle over the Grassmannian, where, you know, the way you think about it is you first choose a plane, and in the plane you choose a degree 2 equation, okay? So we do understand the Hilbert scheme in the case of degree equals 2. And then the conserved space, you know, is a similar thing, right? Typically what it is that it's a degree 2 map from P1 to Pn, right? And sometimes what can happen is that it can break, and then in this case, it's like, you know, in this case, the image is a union of 2 lines. But you see, so let's understand how these two spaces differ. The only place where these two spaces differ, like the Hilbert scheme and the conserved space, is when you have a double line, when it's a non-reduced curve that you have, right? So now what happens in the Hilbert scheme? So if you want to specify a double line in the Hilbert scheme, what you need to specify is you need to specify the line. So you choose a line. And remember, this has to be planar. So in other words, what you need to say that you need to choose a plane that contains that line. And once you choose a plane that contains the line and the line itself, then you write the equation of the plane and then you do equation of the line. Then within the plane is the square of the equation of the line. So that specifies for you that double line in the Hilbert scheme. In the conserved space, how do you get the double lines? The way you get the double lines typically is that you have a 2-to-1 map. So you see, you have a map from an irreducible P1 to a line, typically, right? And this is a 2-to-1 map. Of course, it could happen that, like, this domain curve breaks into two pieces and both map onto the same line. But that's a pretty special thing that happens, and it's in the limit of these things. And how do you specify a 2-to-1 map from P1 to itself? And what you need to do is, of course, you need to specify the ramification points. Such a map typically has two ramification points, 2 points where the derivatives vanish. And if you specify those 2 points, then you've specified the map, right? So if I look at, for instance, the map given by z goes to z squared, that's ramified at 0 and infinity. And if this thing is ramified at 2 other points, then you change coordinates so that those become 0 and infinity, and that's the map. Yeah. All right. So you see that these spaces do differ, right? And they differ much more dramatically as the degree increases. So, for instance, if you look at the Hilbert scheme of twisted cubics, that's no longer irreducible. So there is one component of dimension 12 that parameterizes twisted cubics, but then there's all sorts of other garbage. Like what you can do is you can take a plane cubic curve, which is actually an elliptic curve, and add a point that's floating around. So the Hilbert scheme has lots of junk in it. Whereas the conserved space, as I said, its main nice property is that it's irreducible. So we will often use the conserved space in these lectures. And as I pointed out, the Kim and Pandrapande proved that this is irreducible when the target is a homogeneous variety. Okay? All right, so this is a little sort of introduction to what kinds of compactifications we are going to talk about. When we need to talk about it, I'll say more. But so this is to say, like, what we mean so that you have an idea. So you see, the key point here is that the tangent space, so if you have a smooth rational curve, or even any smooth curve, right? Smooth curve. So the tangent space to these Hilbert scheme and conserved space and so on and so forth, we understand them. Like deformation theory tells you what the tangent space is. In the case of the Hilbert scheme, it's the normal bundle of the curve. And in the case of the conserved spaces, the normal bundle of the map. So now what does that mean? So you see, each time you have a smooth submanifold, right, of a manifold, then its tangent bundle sits in the restriction of the ambient manifold to your manifold. And the co-kernel of that is what we call the normal bundle. Right? So this is the directions, the normal directions. So these are sort of, you have the tangent. So, if you have an ambient manifold, right? And you have a manifold and inside you have an ambient manifold. So there is the tangent space, right? And then at each point, there are the normal directions, right? So this is the co-kernel of the map that puts the tangent bundle of the submanifold inside your manifold. And this normal bundle, you see, by the fact that the tangent space, the Hilbert scheme is the global sections of this normal bundle, tells you the controls the local geometry of the deformations of this curve. Okay. Similarly, if you want to talk about the normal bundle of the map, if I have a map, then the tangent bundle of P1 by the differential of the map maps to the pullback of the tangent bundle of Pn. And then the quotient of this thing is called the normal bundle of the map. So you see, the basic task that I want to sort of handle in this, in these lectures is sort of understand as much as we can these normal bundles, okay? And, the main motivation for this is that understanding these normal bundles is the way you understand the local geometry of spaces of rational curves or spaces of curves in general. So if you want to understand, like, how these curves deform and, what the space looks like around a particular curve, then you need to understand this normal bundle. Okay, so what does it mean to understand the normal bundle? Okay, I mean, so some sort of vector bundle defined by this, right? So you have you look at all the normal directions and they form together a bundle. So we want to know what kind of bundle this is. So what do we mean by this? So you see, we can be pretty precise on P1 when it's a rational curve, what we mean by this. So the main theorem, and this is, usually goes under the name of Birkhoff-Grothendieck's theorem, but I think it's a fairly old statement, and it's this following fact, right? If you have a vector bundle on P1, then it is a direct sum of line bundles. So maybe before I do this, maybe let me just get a page here. Let me add a page here. You see, line bundles on P1, we understand. Every line bundle on P1 is of the form of A for some integer A. So these are all the line bundles on P1. P1 is, by the way, a sphere, yeah? So topologically, it's a sphere, it's the two sphere, right? So OP1 of A, every line bundle on P1 is of this form OP1 of A, where the sections, right? The sections of this line bundle are precisely homogeneous polynomials with degree A. Okay, so in other words, the way you can think of this thing is that, if you take two copies of the plane and you glue them to make the, you make the sphere, and then on this, so, you have the two trivial things, and then the question is that how do you glue in the middle? And then, how you glue is by twisting like T to the A or something like this, yeah? Okay. So now the amazing theorem on P1, and this is very, very special to P1, is that there are no interesting vector bundles on P1. Yeah, and one way you can make vector bundles is that you take the direct sum of line bundles, right? Or any variety, if you take a direct sum of line bundles, you get a vector bundle, right? But most varieties have lots of much more interesting vector bundles that are hard to understand. But on P1, there are no interesting vector bundles. So the main theorem that's known as the Birkhoff-Grothendieck theorem is that every vector bundle is a direct sum of line bundles. What that means is that, there exists, so if you have a rank R vector bundle, there exists a sequence of integers. Let me list them so that they increase like this, right? Such that this vector bundle you have is isomorphic to the direct sum of these line bundles. And moreover, this sequence is unique. If you make it increasing, I mean, the only thing you can do is you can scramble the integers. But if I list them in increasing order, right, then it's unique, okay? The first observation is that the uniqueness, of course, is clear, right? I mean, let me maybe sketch a proof of this thing because it's such a fundamental theorem that everybody should know. So like, let me quickly sketch a proof of this theorem. The first observation is that the uniqueness is clear. I mean, suppose that you have two like this, right? And say that the AIs and BIs for two sequences, right? So let's say that maybe BR and AR are the same, maybe BR minus 1 and AR minus 1 are the same, but maybe at some point they differ, say. Say that BJ and AJ are the first time they differ, right? Up to J, maybe BR and AR are the same, and so on and so forth. Let's say that AJ and BJ are the largest index J for which they differ. Okay. Then, but you see now what you can do is you can take this E and twist it by minus BJ. Right? Well, on the one hand, it's looking like this, and the other hand, it's looking like this. If I twist this thing by minus BJ, you see, I know what the global sections are, right? The global sections of something of the form O of A is the homogeneous polynomials degree A. Now you see on this side, right? Now this looks like O plus O of BJ plus 1 minus BJ, and so on and so forth. On the other side, it looks like O of AJ minus BJ plus the same thing, right? Now you see this has more sections. There's the constants here. This is negative. So there are no polynomials with negative degrees. So that you see the sections would be different, for instance. So that would tell you that these numbers had better be the same. If they were different, then you could tell them apart. Okay? So uniqueness is clear. The whole question is, why does such a decomposition exist? Why is this always a direct sum of line bundles? Let's sort of sketch the proof of this as well. You see, basically you do induction on the rank. Let's do induction on the rank. By the way, I mean, if you have any questions, you can interrupt at any time and ask. Induction on rank. So let's do the following thing. Let's look at the maximal A for which I have a map from O of A to this E, a non-zero map. Okay? Like such a thing exists. The reason such a thing exists is that if you look at E to the A, right, eventually H naught of this thing is not zero by Serre's theorem. If you make A really large, right, eventually you have a section. So that means that you have a map from O to E twisted by A, and that corresponds to a map from O of minus A to E. So there's always in some A that maps to E. Okay, I somehow managed, maybe I should have made this thing B so that we set minus B equal to A. So that you have some non-zero map like that. Okay, so you take the maximal A for which there is a map like this, and it can't be like, there's a maximum, like, if you make this B very negative, then it becomes zero. So you can't have such a map. Okay, so now the observation is that you see this is typically only a sheaf map. But if you have a sheaf map, right, it can vanish at points. Like for instance, you have a sheaf map from O to O of 1, right, given by multiplication by S or something like this, right? And then you see then this vanishes at the point S equals 0, so that you get, O of P, where P is the point defined by S equals 0. So typically, if you have a map of sheaves, right, then it can vanish, and this is not going to be a subbundle. Yeah, they can vanish. But you see, the point here is that because we chose this A to be maximal, then this thing cannot vanish. Now, why is the reason? Because you see, suppose that it vanishes at some point, then I can twist it by that point, and I get a map now, non-zero map from O of A plus 1 to E, right? But this is not allowed because A was maximal, so then this map by the choice has to be always non-zero. What that means is that this is not an inclusion of bundles. It's not just a sheaf map, it's an inclusion of bundles, right? So that means that the co-kernel is also a bundle. Now it's a bundle of rank R minus 1, okay? And now you see you can do induction. Suppose that up to rank R minus 1, I knew that this thing split into a direct sum of line bundles. So then you see I put my E in this exact sequence like this. I have this O of A mapping to E, mapping to this F, which is some direct sum of line bundles. This, of course, doesn't yet show that E itself is a direct sum of line bundles because you can have non-trivial extensions a priori, right? Like, just because you put a bundle in, in an exact sequence with two bundles, it doesn't mean that this splits. But in this case, it has to be split. So what we need to show is that the extension class is trivial. In other words, what we need to say that this X1 group is equal to 0. And if we can say that this X1 group is 0, then there are no non-trivial extensions, and this thing has to be a direct sum. All right, how do you do it? What you do is you twist this thing by minus A minus 1. Let's twist everything by minus A minus 1. So here I have O of minus 1. Here I have E minus A minus 1. And here I have AI's minus A minus 1. Now you see this has no cohomology. No cohomology. No H naught, no H1. No cohomology. Right? On the other hand, I also know that H naught of this is 0. So because you see, if there were a section like this, then I would get a map from OA plus 1 into E. And remember, we chose A to be maximal. So there are no such non-zero maps. So we know that this is 0. It follows that the H naughts of these things are all 0. Yeah. But you see, so that means that the degrees of these, like, you know, this, the H naughts, as I said, is polynomials at this degree, right? I mean, if this is going to be 0, then the degree had better be negative. So we learned that AI minus A minus 1 has to be less than 0. In other words, AI is less than or equal to A. Okay, so now you see what we get is that this X1 group is H1 of OA minus AI, right? So, and we get that there is no higher cohomology in that case, and then we learned that the extension class has to be 0. So the upshot of this thing, right, is that there are no interesting vector bundles on P1. They are all direct sums of line bundles. So in particular, you see, when I'm talking about the normal bundle of a rational curve of P1, right, or any bundle on P1, I can, like, you know, there is a way of knowing what it is, right? Knowing what it is means that you know what these integers are, right? If I know what those integers are, then I uniquely know the isomorphism class of the bundle. All right, so let's just say it like this. So given the vector bundle of P1, we talk about its splitting type. That means that we write this vector bundle as a direct sum of line bundles. We can choose them so that they look like this, so that it's unique, so that I don't have to worry about the reorderings, right? And then you see, to say that you know a vector bundle on P1, that means that can you tell me a splitting type? In that way, I know this bundle uniquely up to isomorphism, okay? There are some pretty special bundles, right? The first one is that, like, you know, we call this bundle balanced, right? If the differences of all these numbers are 1. So, like, let's do an example. So if I have a degree 2 rank 2 bundle, I could have, like, for instance, O of 1 plus O of 1, right? The sum of the degrees is 2, the rank is 2, or I could have something like O plus O of 2, or I could have O of minus 1 plus O of 3, and so on and so forth, right? This one we call balanced because the degrees, the individual degrees, are as close to each other as possible. Okay, so, you know, if you had rank 3, so, and degree 2, for instance, you could have something like this. It could be O plus O of 1 plus O of 1, or it could be O plus O plus O of 2, and then, you know, you can imagine different things. So this one is the balanced one. The pairwise differences are as close to each other as possible. And then you call it perfectly balanced if all the numbers are equal. Of course, to be perfectly balanced, then the rank has to divide the degree, right? If the rank does not divide the degree, then you cannot be perfectly balanced. Okay? All right. Okay. So this is a little background on vector bundles on P1. So now let's go back to our questions. So we have some sort of variety. Yeah, say that you have X, some sort of smooth projective manifold. And we have our rational curve in here. So this is our rational curve, smooth. Okay, smooth rational curve. So then you see there's some bundles associated to the situation, right? The first is that I can take the tangent bundle of X and restrict it to C, right? And then the other thing, as we said, you can look at the normal bundle of X and C. So given a curve in the space, or given any manifold inside another manifold, right, you automatically have like 2 bundles associated to this. And these are the most important bundles, you know, for the differential geometry of this submanifold. One is the restriction of the tangent bundle. I mean, of course, you also have the tangent bundle of C, and, you know, in general, that's a more complicated thing. In the case of P2, it's a line bundle and it's isomorphic to O of 2, right? The tangent bundle of P1 is O P2, O P1 of 2, right? You know, if you give yourself a vector field on the sphere, then it has 2 zeros, right? A general vector field on P1, a holomorphic vector field, has 2 zeros. Yeah. Okay. So what you see from this is that, like, you know, there are 2 bundles. You know, given a submanifold of a manifold, there are 2 bundles that are immediately associated to it that control most of the differential geometry, right? One is the tangent bundle of the ambient manifold restricted to C, and as I said, the other one is the normal bundle. So in our situation, when we have a rational curve, right, immediately the 2 questions you can ask is that what are the splitting types of these? And as I said, like, why do you really want to know about this? Going back to sort of what we were saying, right? The deformations of the space of these rational curves is determined by this global sections of this normal bundle. Once we know the splitting type, right, we know exactly what this global sections are. So it's really important for us to understand the local geometry of the space of rational curves for us to understand the splitting types of these normal bundles. All right. So that's the situation. Again, like in the next lectures, I'll talk about what happens when X is not projective space, but let's just start from the very easy, like, you know, at least easier to understand case of projective space, yeah? And the basic question, as I said, is that what are the splitting types of these bundles, okay? Just to summarize, so what have we said so far? We said that the rational curve is a map from P1 to your variety, and associated to this, there is a normal bundle and the restrictions tangent bundle of the ambient variety. And we learned that every vector bundle on P1 is a direct sum of line bundles. And so is determined by a sequence of R integers if R is the rank. So then the question is, what are these integers in this case? So let's compute some of these things, okay? Let's compute. All right. So what's our situation? We have our P1, it's mapping to Pn. This is a map of degree D. So in other words, it's given by n+1 polynomials like this. These are in the coordinates of P1 ST if you want. So these are degree D polynomials, no common roots. And we can further impose that maybe the image is smooth. So that means is that if you form the Jacobian, the rank of that matrix never drops, okay? So we said that the tangent bundle of P1 is all P1 of 2. So the degree of this one is 2. Now, what's the tangent bundle of Pn? So let's just say the tangent bundle of Pn. We understand the tangent bundle of Pn by the Euler sequence. So you see, you have the map, O goes to O1 n+1, right? This is the map given by x0, x1, ... xn, right? And the co-kernel of this is what we call the tangent bundle of Pn, right? That's the tangent bundle to Pn, right? So in particular, we see we know the degree of this thing. So the degree, so the degree, or let's put the determinant if you want. If I take the determinant of the tangent bundle of Pn, you get OPn of n+1, right? The degree of this thing is n+1. Yeah, this has degree 0, this has degree n+1, so this has to have degree n+1. Now you see, if I pull this back, I'm pulling this thing of degree n+1 by a map of degree d. So that you see that this has degree d times n+1. Since the degrees are additive, so you learn that the normal bundle to the map has to have degree d times n+1 minus 2. And what's the rank? Projective space is n-dimensional, so the tangent bundle has rank n. P1 is one-dimensional, its tangent bundle has rank 1, so the rank of the normal bundle is n-1. So you see, so what we are trying to understand is a vector bundle of rank n-1 and degree d times n+1 minus 2, okay? So now the point is that I can write this normal bundle, you see, like this. Let me write it as d plus bi. And then, you know, just by counting, like, you know, just doing this, the degree of this thing is d times n-1 plus the sum of the bi's. And it's supposed to be d times n+1 minus 2, so that the sum of the bi's has to be 2d minus 2. Okay, so let me write it like this. Let me put a d there. That will just simplify, you know, rather than always writing as d plus something, I'll just write as d plus bi, and I'll think about the bi's. Okay, so what we have is that we can write our normal bundle like this, and the sum of these bi's is 2d minus 2. And what is it? Okay, let me make one other sort of highbrow remark. Okay, if you have a bundle on P1, you know, So this is the kind of things like, you know, so somebody walks up to you and says, you know, guess what bundle I have on P1 without giving you for any other information. You know, your life depends on this. You know, tell me what bundle you have on P1. What would you guess? And of course, what you would guess is that the bundle would be as balanced as possible, right? So now what does that mean? You see, there is like a versal deformation space of the space of bundles. So, you know, if you have a bundle, right? Say that you have a bundle on P1, then there's a versal deformation space. So that means that you look at the deformations of this bundle. And the question that you can ask, like, you know, if you start with a bundle and you deform it a little bit, what bundle is it likely to become? Yeah. So this, you see, I mean, the way to think about this, of course, the most common thing that can happen is that the bundle is balanced, and then it's usually as balanced as possible, right? So if somebody tells you that I have a bundle, guess, then you should always guess that the bundle is as balanced as possible. Of course, you might not win, right? It might not be as balanced as possible, but you know, if your life depends on this thing, your chances are very good, much higher if you guess that it's balanced, unless you know some other information, right? So in fact, you can compute in the versal deformation space of the bundle what's the expected dimension of a certain splitting type. And you see, if you give yourself a bundle like this, right, then the codimension of this locus in the versal deformations type is given by you know, age one of the endomorphism bundle. So in other words, what you do is you look at age a minus ai minus 1, and you sum these up over all ij where ai minus aj is less than or equal to minus 2. Okay? So that you see, if you have a balanced one, then this thing is going to be 0. So like, you know, the general point in the versal deformation space is balanced. So like, for instance, if you started with something like O plus O, right? Then in codimension 1 in the versal deformation space, it will look like this. In codimension 3, it will look like this. In codimension 5, it will look like this, and so on and so forth. So it's much less likely that you have such an unbalanced bundle. Of course, you know, as long as you go deep enough in the versal deformation space, you'll see all deformation types. But the one that's most common is the balanced one. Okay? And so you see, the basic question that I can ask is that I have the space of rational curves in projector space, right? And I have these two bundles. I have the normal bundle and the tangent bundle. So what is the splitting type, and in what codimension do these splitting types occur? Do they occur in the dimension where you expect them? Yeah. So the question is, do the given splitting types occur in expected codimension? Okay, so that you can take this to be the sort of motivating question for these lectures. And now we'll see the geometric applications and why we care about it. Okay, so far I've babbled and babbled and babbled, and I've not computed the normal bundle for you. So let's compute the normal bundle, okay? So here is what we are going to do. So I will assume here that my characteristic is either 0 or does not divide the degree. And say that you give me a rational curve, and I want to compute the normal bundle of that, right? So let's compute what the normal bundle looks like. How do you compute normal bundles? So now the task that I have is to actually convince you that this is multilinear algebra and you can do it. Yeah, it's not something scary. You can really do this. So let's do it. So suppose, so I need to give you what the curve is given by. So let's say that it's given like this. So my map is s to the d minus 1t, s to the I2, t to the d minus I2, and then all the way you end with s t to the d minus 1 and t to the d. The reason why I'm taking this to be s to the d minus 1t and s to the d minus t d minus 1t to the d is that I want to make the curve smooth. I want to make sure that the curve is smooth. All right, so you gave yourself some monomials like this, right? So it's a degree D rational curve, and I want to know the normal bundle of this map. Okay, so the claim is that the normal bundle of this is like given by this. So you look at the pairwise difference. So like, you look at the differences, you do D minus I2, D minus 1 minus I3, I2 minus I4, and so on and so forth, right? So you look at the differences, skipping one over, right? You get n minus 1 terms like this. Then the claim is that the normal bundle is D plus these differences, okay? Is the statement clear? I have a curve given by monomials like this. I insist that the first is SD and SD minus 1t, and the last two terms are STD minus 1 and TD, and I don't tell you what happens in the middle, right? And what we want to say is that, and here I want, I guess, D to be bigger than or equal to N. And as I said, I want the characteristic of the base field to either be 0 or not divide D, okay? Then how do you compute this thing? So here I'll show you a useful way to compute. Again, whenever the characteristic does not divide D, right? Then you see you have exact sequences. So let me see what I can get. Let me just maybe get a map. Let me get a page here. So you see, we have two, let me rewrite this exact sequence. We first have the Euler sequence for the tangent bundle of P1. Right, so this is the Euler sequence for the tangent bundle of P1. So this gives by ST, that's the matrix given by S and T. So this is the Euler sequence for the tangent bundle of P1. And the other thing that you can do is you have the Euler sequence for the tangent bundle of Pn, right? And you can pull it back. All right, so now how is this given? You see the tangent bundle for the Euler sequence for the tangent bundle of Pn is given by x naught, x1, dot, dot, dot, like that, right? If you pull it back, that means that you plug in your f naught, f1, dot, dot, dot, fn, right? And then you see here, the map is given by the derivative. This is the differential, right? So what do you need to do? Like, so this matrix is given here by, what is that? The Jacobian matrix. So like, let's see. So I always get these things backwards. I think we should do it like this, yeah? So you have df naught ds, df naught dt, df1 ds, df1 dt, right? And dot, dot, dot, dfn ds, dfn dt, right? Wait, there is a question. Are the ij in any particular order? Yes, I mean, this started as I naught, then I1. This is the coefficient of SD. Here. These are the coefficients of SD. Oh, did I do it backwards? I did it backwards. It's a typo. That's better. Is that the problem? Yeah, they should be bigger than 2, not less than 2. Yeah. All right, thanks. All right, coming back to it, we have our Euler sequence here, our Euler sequence here. This is the Jacobian matrix that you put here. And then you see Euler's relation says that you can make this thing commute by multiplying here by the degree. That's why I need the characteristic to not be 0. So this gives you an isomorphism like this. Then you see if you change the sequence, then here I have the normal bundle of F, and this becomes the normal bundle of F. Yeah. In other words, this normal bundle, right, you can compute as the co-kernel of this Jacobian matrix. So the normal bundle of F is nothing other than the co-kernel of the Jacobian matrix. And I always, you know, I never know whether you should write it like this or you should take the transpose. So I'll call both the Jacobian matrix. So like both itself and the transpose, okay? So luckily I don't teach multivariable calculus that frequently. Otherwise, I think the kids would never learn what. And then you see, why does this commute? This commutes because of the Euler relation, right? Like if I have S times the derivative plus T times the derivative, that's the degree times F, right? Again, you can use this method to compute the normal bundle if the characteristic does not divide D. And like it is a quotient that if the characteristic divides D, then you have to be more clever, right? You can't just use this method. You have to work hard, a little bit harder. And in fact, like, you know, we will talk about what happens in positive characteristic next lecture a little bit more. But for this lecture, let's pretend that our characteristic is 0. We're over the complex numbers, or our characteristic is sufficiently large that it doesn't give a headache, okay? So now, in other words, to say that you can compute this normal bundle, I just need to compute the co-kernel of this Jacobian matrix, okay? Let's do it. You see, here is the secret to all life, right? Co-kernels are hard to compute. Kernels are easier to compute, even though it's the same thing. I don't know why, but so is life. So, you know, just dualize this thing. So it's a little easier if you dualize it. And this is, I think, a psychological thing, because at the end of the day, it's the same exact thing. So you take your Jacobian matrix, you transpose it, and you dualize everything, right? And then now we want to compute the dual of this normal bundle, or the kernel now. For some reason, kernels are easier to compute than co-kernels. I don't know why. It's a psychological thing, as I said. So now you see, I have this matrix, right? So in other words, you have this matrix. Now it looks like df not ds, df1 ds, dot, dot, dot, dfn ds, right? And here it means df not dt, dot, dot, dot, dfn dt, right? The question that we are asking is, what are the relations among the columns of this matrix, right? That's what it means to compute the kernel of this matrix. So the question is, like, what are the relations? Among the columns. In other words, you know, what are the syzygies of these columns? So we can find those, right? So now let's look at our thing, right? Let's take our derivative. The map was, where was the map? The map was like this, right? S to the d minus 1t, and so on and so forth. So I take the d derivative. This is d times s to the d minus 1. The t derivative is 0. Then it's d minus 1 s to d minus 1t. Then the t derivative is s d minus 1, and so on and so forth. So you write this matrix, okay? So then the question becomes, what are the relations among the columns of this matrix? And I claim that, you see, some relations are easy to see, okay? Let's see some of the relations. So if I look at 3 consecutive columns, so let's look at the triples of consecutive columns, and then I claim that then there are some relations. Okay, this is a lot of indices, and it's a little bit hard to explain on Zoom and stuff, so you have to believe me a little bit, right? So you see, like, it looks like the S column, the first column looks like S to the ij minus 1, t d minus ij. The next one is S to the ij plus 1 minus 1, d minus ij plus 1. And this ij plus 2 minus 1, d to the minus ij plus 2. Yeah, there are, of course, coefficients here. Like, you know, if you take the S derivative, this is ij plus 1 and ij plus 2. And if you do the t derivative, then it becomes S to the ij t to the d minus ij minus 1. Here it's S to the ij plus 1 t to the d minus ij plus 1 minus 1, and so on and so forth. Okay, and again, now we are differentiating the t, so we have a d minus ij, d minus ij plus 1, or whatever. Okay, so forget about the coefficients first. You see, if I multiply this thing by t to the ij minus ij plus 2, this one by s to the ij minus ij plus 1, t to the ij plus 1 minus ij plus 2. Anyway, you see, like, if you multiply this thing by the correct t, this thing with the correct s and with the correct t, and this thing with the correct s, right? Then you can make them all be equal. Yeah. All right. Yeah, it's not so hard to see. This becomes t to the ij minus ij plus 2, which is what we have here. Here it becomes t to the d minus ij plus 2, and the s becomes the same. And similarly, you can make the coefficients match too. I think you take these things anyway. If you don't take these things, you can fiddle it a little bit. And so the key point here is that you see there are these triples of, like, whenever you have a monomial like this, triples of columns have these relations. And so you know what it is that then I can write this matrix here. I don't know what you call it. We should call it A. And you see, so you see, if I put t to the I2 minus I naught, s to the, you know, I don't care what this is, then s to the I2 minus I naught with these coefficients that are non-zero, right? And then t to the I3 minus I1, s to the whatever it is, then s to the I3 minus I1, and I go like this, right? Then the next one is t to the I4 minus I2, s to the something, and then s to the I4 minus I2. And I go like this, right? Then you see, if I take this matrix A, right, and then compose it with this M transpose, or Jacobian matrix, Jacobian transpose, we get 0, right? Because these are relations among the columns of this matrix M, okay? What that means, right? What that means is that if I look at the kernel of this map, then this, right, this bundle lies in it. There is a map from this bundle to this kernel given by this matrix A, right? Because, like, you know, A composed with this Jacobian transpose is equal to 0. That's how we got this matrix. But, you know, in general, you can really easily ask a computer to compute the relations among the columns of this matrix. And, you know, as long as the matrix is relatively small, the computer will spit this thing out to you immediately. Yeah. In this case, we can do it by hand. Yeah. All right. Now you see, I claim that the dual of the normal bundle is equal to this. Now, why is that? Why is that? The reason is like this. So the first thing is that this matrix, so you see, we have an inclusion of this to the kernel. But what I want to say that this is an isomorphism. I want to say that this A is an isomorphism. But you see, A is a very special matrix. It's everywhere in full rank, right? A is everywhere full rank. Now, why is that? You see, like, let me look at this minor. If I look at this minor, you see, like, if I look at this minor, like the beginning minor, right? Then you see this is like an upper triangular matrix, and the diagonal entries are all powers of t. So then you see, if I take the determinant of that minor, then you get t to some power with the coefficient not being 0, right? I mean, the coefficients are like a product of things like I2 minus I naught, I3 minus I1, and so on and so forth. Yeah. So you see that this minor vanishes only when t equals 0. So that we get that, you know, this is a full rank matrix everywhere except that t equals 0. And then, you know, what you can do is look at this minor. If I look at this minor, right, then this is a lower triangular matrix, and then, you know, along the diagonal, I only have powers of s, so then I get s to the n with some non-zero coefficient. And then you see that that one doesn't vanish when t equals 0, because it only vanishes when s equals 0. So there you see that this is an injective map of vector bundles, right, of the same rank and same degree, so that you conclude that it's an isomorphism. So that we've computed the normal bundle. Here I think I wrote it right. That's ij minus ij plus 2. Before, I think I'd written it wrong. Yeah. Here I wrote this correctly, and I go from j equals 0 to n minus 2. All right, I never wrote it right, but close enough. Okay, so in particular, you see this computes for you the normal bundle of these monomial curves. And in particular, if you have a rational normal curve, this is an important piece of information. If you have a rational normal curve in Pn, again, that means that it's given by s to the n, s to the n minus 1t, s to the n minus 1t squared, and so on and so forth. Then by what we said, the normal bundle is on plus 2 to the n minus 1. In other words, a twisted cubic in P3 has normal bundle O5 2 copies. Rational quartic has O6 3 copies, and so on and so forth. A line is always O of 1 to some bunch of powers. Okay. All right. So this gives you at least a way of computing this, but in general, you can use multilinear algebra to compute this thing. What you need to do is you need to find the Jacobian matrix and find the relations among the columns of this thing. So, it's something that you can do, and you know how to do from linear algebra. Okay, that's good. Oh, let me make a quick remark. I mean, it can happen that the rational curve can be degenerate, right? So that means that the span of the image is a smaller dimensional projective space. Then you see what happens is that then it's not very interesting what happens. Like then if you know the normal bundle of the curve in this PD, then you also know it in this PN. So if this bundle is written like this, then you see the normal bundle of the PD and the PN, that's a linear space, right? So it's a bunch of pullbacks of O of 1, so that's a bunch of O of E's. There are no interesting extensions here, so that, it just splits as the normal bundle of the curve in PD plus this O of E to the n minus d. So that you see, you can always assume when you're doing these things that you're working with a non-degenerate curve. If the curve is degenerate, then you just compute the normal bundle in a span. So that's something to say. Okay, so this was an example, and I hope sort of it gave you a sense of how you can compute these things. I mean, if you get nothing else out of these lectures, you should get that, if you're given a rational curve in projective space, then at least in characteristic 0, or if the characteristic does not divide the degree, then you can compute the normal bundle of this thing by some linear algebra. And the linear algebra is that you look at your Jacobian matrix and then you look at the relations among the columns of this matrix. Okay, but so let's come back to our question. So this told us how to compute things, but let's go back to our question. Our question was, what are the possible splitting types of the normal bundle of a rational curve or the tangent bundle and so on and so forth? And in what codimension do they occur? Okay, so let's do this. So let me tell you a construction. This is a construction due to Sacchiero, okay? And it says the following thing. Suppose that you make the BIs be at least 2, and then the sum be 2e minus 2. So that's what we needed, right? So that was necessary condition, so to speak. Then there exists a map from P1 to Pn unramified, right? Such that the normal bundle is given by this, right? In other words, what this is saying is that all possible splitting types do occur, okay? Remember that these were the restrictions from the degree considerations. So, the degree and the rank of this thing is determined, and I'm making this thing be non-degenerate, right? So the way you should think about this is that all possible splitting types occur. In particular, you see the generic splitting type is balanced, right? So the balanced splitting type occurs, and so, that's the generic one, So in other words, what you learn from this thing is that if I have if you pick a random rational curve in projective space of degree at least n in projective space Pn, then the normal bundle of that is going to be balanced. And then, all allowable splitting types also occur. You can find a map like that. Okay, let me explain the construction, which is kind of cute and not as well known as it should be. So I'll explain it a little bit. There are some indices and stuff involved. So maybe I'll do it in a way that I skip the indices and then you can check these things for yourself. Yeah. So this is due to Sakiro. Let me point out that this is false in characteristic P. Yeah. If you have, for instance, a general curve, rational curve of even degree in P3, then the normal bundle in characteristic 2, the normal bundle is not balanced. Okay. It turns out that in that case, and you see that this thing fails, right? Like, because it's even degree, 2 divides this degree. So then what happens is in that case, actually the normal bundle twisted by 1, or the dual of the normal bundle twisted by 1, is the pullback of the Frobenius by, so, it's, so that all the integers have to be divisible by 2. And then you see what, if you look at it, then in fact, what you can prove is that, in characteristic 2, then the general splitting of a normal bundle is like this. For an even degree rational curve in P3 is 2e minus 2 plus 2e instead of 2e minus 1 and 2e minus 1. The reason for this thing is that one of these bundles or a related bundle has to be the pullback of the Frobenius, so that all the degrees have to be even. So, in characteristic P, this kind of thing can be messed up. So you have to be a little bit careful. So as I said, when I'm saying this, I'm either in characteristic 0 or my characteristic is large enough so that this calculation is applicable. Okay. Back to Sakiro. So now you see we have some B1, B2, Bn minus 1, and we want to make a map like this, right? So I need to exhibit for you a map with this kind of splitting type. And the way we are going to do our calculation is, again, similar, like we'll do it similar to the monomial case. And the map will be almost monomial. You can't quite do it with monomials, but the example will be like similar to monomials. Okay, so then you define some sort of numerics. Don't pay too much attention to these numerics. They are defined so that they'll work at the end, okay? But just to be precise, you set delta 1 equal to 1 and delta I to be equal to bi minus 1 minus delta I minus 1, okay? Whatever these things are, and you set your C to be equal to this thing. All right, so this is some numerical trickery, so forget about this. When we need it, then we'll come back to it, okay? So now you choose two polynomials, two general polynomials. They both have degree E minus C. C is this number, okay? And these have to be general enough, like, like you can be precise about what general means, but I don't need to worry about things like, they shouldn't have common roots. They shouldn't be divisible by T and S. They should have no repeated roots, and things like this. You can specify some finite number of easily determinable conditions from the argument. But anyways, you just choose two random polynomials P and Q. Okay. So now what you do is you set a bunch of integers, and again, it doesn't matter so much what these things are. It has to do with the data that you're given. Right, so ki is going to be c minus the delta j's going up to I. K naught is going to be c. K1 is c minus delta 1. K2 is c minus delta 1 minus delta 2, and so on and so forth. Okay. All right, once you set it up like this, then the map you look at is this. You do s to the k naught p. So you see this had degree e minus c. This is c, so this has degree e. So the curve will have degree e here. Then you do s to the k minus 1, t to the c minus k minus 1, p, all the way to s to the kn minus 1, t, c minus kn minus 1, p. So, up to here until, okay, you can't, if I cover it, we're not on the board. So let me circle it. Up to here, like, if you don't have that last term, right, this is like a monomial map multiplied by this polynomial p. Then for the final coordinate, you put t to the cq, where q was this other polynomial we chose, okay? And that's my map, okay? So f goes s to the cp, t to the c minus 1p, it goes like this, yeah? All right. Again, I mean, how are we going to compute the normal bundle of this map? So the claim is that the normal bundle of this map is given by this, what we said. Yeah. So we want to say that that really gives me the splitting, provided that the b's are at least 2 and so on and so forth. Where was the theorem? Provided that the b's are at least 2 and the sum is 2e minus 2. Okay. Okay, so now how do I do this? I mean, we learned how to compute the normal bundle, right? What we are supposed to do is we compute the Jacobian matrix, right? So the Jacobian matrix is ki s to the ki minus 1 tc to the minus ki p plus the s derivative of p, right? And then you have to do the t derivative plus the t derivative of p. So it looks like this, okay? You see, I mean, it's very similar to the previous calculation that we did, but before, like every triple of columns, right, satisfied a relation. Now here, only the first n only in the first n minus 2 columns, every triple of columns, every consecutive triple of columns satisfies a relation. And again, what's the relation? The relation is, you know, you multiply the first one by t to the ki minus 1 minus ki plus 1 with this coefficient. The middle one by s to the ki minus 1 minus ki t to the ki minus ki plus 1. And the last one by s to the ki minus 1 minus ki plus 1, okay? Anyway, the indices don't matter. If you write this down yourself, you'll immediately see what to do. It's probably much easier for you to do it yourself than to follow on Zoom what I'm talking about, yeah? But the key point here is that if you have this thing, then the first like the first 3 columns, the next 3 columns, and so on and so forth, after the like, you know, except for the last column where we have this extra q that we put in, like the consecutive triples of columns all satisfy the same relations that we had in the monomial case, okay? In other words, what this means is that, you see, if we write our matrix like this, right? So we have our O of minus e to the n plus 1 going to O of minus 1, given by this Jacobian matrix or its transpose. And here we have the normal bundle of the map dual, right? So we are trying to find the relations among the columns of this matrix, right? And we know that we have an injection of bundles from O of minus e minus ki minus 1 minus ki plus 1, now n minus 2 copies to this dual of the normal bundle. Again, you see, if you write this matrix, right, there are t's only down this diagonal and there are s's only down this diagonal, right? So that this matrix always ends zeros here. So this matrix always has full rank. So it gives you an injection of vector bundles from this to the kernel, which is the normal bundle. Okay. Okay, but now you see, the nice thing is that, let's see what happens if I do k naught minus k2, right? If you do k naught minus k2, if you do k naught minus k2, you get delta 1 plus delta 2, right? And then what's delta 1 plus delta 2? Delta 1 was 1 and delta 2 was b1 minus 1, right? So that 1 plus b1 minus 1 gives you b1, right? So then you see that this thing was built so the k naught minus k2 is b1, k1 minus k3 is b2, and so on and so forth, right? So that was why you needed all this trickery with the numerics, right? In other words, what this is saying is that this normal bundle dual has an injective map from this O of minus b minus bi. And then the co-kernel, so this is rank n minus 1, this is rank n minus 2, so the co-kernel is rank 1. Well, what's the degree? I mean, we know what the degree is, right? The sum of all these things, e plus bi's. So you see, the sum of e plus bi's is the degree of the normal bundle, right? So the sum of minus e minus bi's is the degree of the dual of the normal bundle, right? So what's left over here is minus e minus bn minus 1. Now, of course, again, we have the problem that, you know, there's no reason why this thing should split like this, because, you know, there could be a non-trivial extension. So we need to check that there are no non-trivial extensions. Okay. All right, so now we compute the extensions of this thing. So you see that this is given by, h1 of bn minus 1 minus bi, the sum of these things. But, we chose so that this bn minus 1 was bigger than the bi's, so that, there is no h1 of this thing, so that you see that there are no extensions. And then you get that the normal bundle is given by this. Okay. All right. So this should already alert that the geometry of the space of rational curves, even in projective space, is not that simple. You see, I'll say this thing as trouble in paradise. Okay. So let me take that n is at least 6, so that I'm looking at rational curves in Pn where n is bigger than or equal to 6. And let me assume that this holds, right? This is some numerical thing, and you'll see why it's like this. So here is what I could do. Let me ask, what's the expected codimension, right, of the splitting type that looks like this? So I have n minus 2 copies of e plus 2s and 1, 3 minus 2n plus 2. Let me convince you that this thing is okay, right? Like 2 plus n minus 2 copies of 2 plus e minus 2, sorry, 2e minus 2n plus 2, right, becomes 2e minus 2, right? So this is really an allowable splitting type. And by what we just said, there are some maps that have the splitting type, right? But okay, so let's look at the expected codimension of this splitting type. Well, we know what the expected codimension of the splitting type is, right? Because it's given by this, right? We know how to compute that, right? And this is like the space of rational curves, right? We said that the space of rational curves was this thing minus 4, right? Okay, so you see what this is saying is that the expected codimension of this, the expected codimension of the splitting type is bigger than the dimension of the space. So the splitting type should not occur, right? If everything was as expected, you wouldn't want this splitting type to occur. And by the way, this inequality can easily be satisfied, right? I mean, like, if you make E large enough, when n is bigger than 6, you can easily see that you can make this inequality hold. So you see that what we see is that by assumption, the codimension is bigger than the space of rational curves. We expect it to be empty, but it's not. I mean, by Sakhiro's argument, we showed that there are such things. So this should already hint at you that there is some trouble in paradise. So like even then for rational curves in projective space, right, the splitting types, is not maybe as expected. So let me maybe, since time is running short, let me maybe summarize a little bit what's known about these splitting types. So first, there is a theorem of Mire that says that if you look at the splitting types of the tangent bundle, pullback of the tangent bundle, then you see that has the expected codimension and is irreducible. So if you just are looking at the splitting types of the tangent bundle to rational curves, the restriction to tangent bundle to rational curves, that behaves like you expect. Like it has the expected dimension given by this, and it's an irreducible space. So that if I specify the splitting type, I get a reasonable locus. Okay. There, the reason turns out to be that, if you pull back the Euler map, you can work out the Kodaira-Spencer map from the tangent space to the, from the tangent space, from homomorphisms to this, to the deformations of the tangent, of pullback of the tangent bundle, and it turns out to be surjective. Then there is a theorem of Eisenbud van de Ven and Gione-Sakhiero, which says that if you look at the splitting type of the normal bundle, but not only for space curves, if you just look at in P3, then that also has the expected dimension and is irreducible. Okay, so for curves in P3, rational curves in P3, life is okay. Okay. And then in the same paper where they proved these things, Eisenbud and van de Ven conjecture that the same is true for Pn. I mean, it's a little bit hard to tell from the way they write in the paper what they mean. In fact, like the statement is something like this. The generalization of the same fact to projective space is so trivial that no self-respecting mathematician would bother to write it down or something like this. So some statement like this that's a little bit hard to parse exactly what it is that they're conjecturing, but I think maybe the read for this is that they're conjecturing that the same is true for Pn. And we've already seen that this is not correct, right? Because these loci do not always have the expected dimension. So maybe let me sort of point out that, in fact, this conjecture is maximally false. So this is work with Eric Riedel. Suppose that you take n be at least 3k minus 1 and you make the degree of the curves bigger than this. Again, these numbers are not so important. It's just like you just should remember that there are some numbers. Okay, then you see I can look where the splitting type of the normal bundle, right, has k copies of E plus 2. And then otherwise is as balanced as possible. The rest is as balanced as possible. In other words, you find the remaining degree and the remaining rank and you divide it and you make them as equal as possible, okay? Then the statement is that that locus has at least k irreducible components. And they are typically of different dimensions and things like this, okay? And, you know, I'm not going to go through the construction. One is because I've already given you too many indices and I don't want to give you any more indices. But the construction is similar to Sakharov's construction. I mean, now you see the kind of game that you play is that, you know, you make some conic relations. And there is a difference whether your conic relations look like this or they look like this. What does that mean? You know, you can have some conic relations where the plane are this, like, you know, their planes intersect and look like this, or they look like this. They're in disjoint planes, right? So this is the case when you have two conic relations, right? And then you can count matrices that have such sort of conic relations to prove this theorem. And if you do this, you see the dimension where you have this kind of overlapping conic relations is much larger, typically, as e goes to infinity is much larger. It looks like e times n minus 2 plus 5n minus 3 compared to e times n minus 3 plus 7n minus 6. You see, if e is very large, then the leading term dominates and you can get separate components. In fact, if you just want 2 degree 2 relations, then that has exactly 2 components, and these are the shapes that they can have. But anyway, but the thing to understand is that we don't understand the components and the dimensions, even in projective space, of a given splitting type for the normal bundle. Okay? Maybe so that's the question. The question is, can we classify the irreducible of components of the morphism from P1 to Pn where the normal bundle has fixed splitting type? Okay? You know, increasingly in the next lecture, I'm going to talk about rational curves and other varieties and computing their normal bundles there. But, you know, you can ask these questions no matter what variety you give yourself. So you give yourself a smooth projective variety, say that it has lots of rational curves, like, you know, the varieties that people especially study are Fano varieties, for instance. These rational curves really control the geometry, as we're going to see next time, right? And you can ask the same question: what's the dimensional space of rational curve? Is the space irreducible? What is the generic splitting type of the pullback of the tangent bundle or the normal bundle? Which splitting types are possible? Almost always these questions are open, you know? And whenever somebody proves a complete answer in one of these things, it becomes an important theorem, right? Let me just point out that, even for simple varieties, the analog of Mire's theorem is also false. So let's point that out. So this is an example due to Sayanta Mandal. Let me look at the Grassmannian. So the Grassmannian GKN is the space that parameterizes k-dimensional subspaces of an n-dimensional vector space. Now you see the key fact about this that we are going to use is that the tangent bundle of this variety has extra structure. It's a tensor product of two bundles. Now, what's the Grassmannian? So the Grassmannian parameterizes k-dimensional subspaces of an n-dimensional vector space. So you see, it has a tautological bundle to a k-dimensional. So you know what is a vector bundle? You just, so you know, if you have a k-dimensional vector space here, right? What does S specify? The fiber over S is just a k-dimensional vector space. That's why it's called the tautological vector bundle. And then you see it sits on in an exact sequence like this. So you have the trivial bundle of rank n, right? So you have S as a sub-bundle of that trivial bundle, right? For W, you specify the subspace W, and then you have the quotient. So you see this variety has two tautological bundles, the tautological sub and the tautological quotient bundle, and the tangent bundle of this variety is S dual tensor Q. So you see there's this extra information, right? So then you see if you have like a rational curve in the Grassmannian, so let me say it like this, the rank of S dual is K, the rank of Q is N minus K, right? So that, and say that you have that the pullback of these things are E, the degrees are E, right? If neither K nor N minus K divides E, then the pullback of the tangent bundle cannot be balanced. So you see that for the general curve, it doesn't have to be balanced. So, you know, if you want to make a real example, like, you know, you take the Grassmannian of lines in P3, G24, two-dimensional subspaces of a three-dimensional vector space, and you look at the degree 3 rational curve. Typically, S dual and Q split in a balanced way. So they split as O of 1 plus O of 2 and O of 1 plus O of 2. But you see their tensor product now splits as O of 2 plus two copies of O of 3 and O of 4. So it's not balanced. It's not O of 3, 4 copies. Yeah. So that you see that most varieties can have like serious differential geometric or algebraic geometric properties that really do influence how these tangent bundles and normal bundles split. And in return, that really influences the deformation space of the rational curves within this variety. Anyway, so next time, let me stop here. It's already an hour and a half, and I've given you too many indices than I should have. So next time I'll talk about like what rational curves look like on hypersurfaces in projective space, and what are the consequences of how they look. Let me stop here.
All right, thank you very much. Any question? So Eric asked about whether I and J are in particular order.
Yeah, I think I sort of fixed that. I think I had a typo.
Oh.
Yeah, I think I fixed that. This was, where was it? It was here, I think. Here. I think I had like the first, like, you know.
Oh.
Is that okay, Eric? Yeah, okay.
Okay, all right. I think so. Any other question? All right, then see you tomorrow morning at the same time.